Hey, so what we did in our last video was to center our two terms that were used as predictors, compute an interaction term, and run a regression. And the equation that we got was a constant or intercept of 26.8, an effect for centered attractiveness of minus 1.8, which was significant, a non-significant effect for centered just world of 0.715, and a interaction term of minus 0.397. So how do we get the simple slopes? We're going to go to process really quickly here, but before we do, and without a full explanation, I'm going to note that back in 1991, when Aiken and West published their book on analyzing interactions of continuous variables in regression, there did not exist a program like Process, and nor did there exist the Johnson-Neiman technique. The trick that was used was to change the 0 point. Change the 0 point. Here is an example program of doing that. This is a generic program that makes X the predictor, centered attraction, Z the moderator, centered just world. It specifies the standard deviation of the moderator, and it basically defines Y as the sentence. Then it goes through and it actually alters the 0 point. So to be one standard deviation above on Z, you take and you subtract the standard deviation of the Z variable from Z. And what that does is it moves the standard deviation. Now, why you subtract, I am not going to try and get into in this video. It's going to take me too long. I think it's going to be frustrating. So I think, if anyone wants to ask me about that, I really enjoy talking about that puzzle. And I might do a little video separately, but it changes what the 0 represents. And subtracting the standard deviation actually changes the 0 to where it represents not the mean, but one standard deviation above the mean. The next line, by adding the standard deviation, changes Z to where it doesn't represent the mean, but one standard deviation below the mean. You then compute the interaction terms with those values of 0 being either above by one standard deviation, below by one standard deviation, or at the mean. And then running this program, which basically runs the regression 3 times, below the mean, at the mean, or above the mean. You get the following. So here, when Z is below the mean, this intercept is the correct intercept of your equation. This slope is the correct slope of your equation, and it's non-significant. So attractiveness was non-significant when just world beliefs are below the mean by one standard deviation. You don't have to pay attention to anything in the latter two terms. Just the 24.8 is the intercept. This is just slope. The slope is not significant. You go down here to the average. 26.8 is your intercept, minus 1.8 is your slope for attractiveness, and it is significant above the mean by 1 standard deviation on Z. 28.7 is your correct intercept, minus 2.871 is your correct slope, and it is statistically significant. Okay, let's move to process, knowing that the way that the Johnson-Neiman technique works is to actually do a more fine-grained manipulation of where the 0 point is. This becomes a nice little trick, because any question that you're asked about where significance lies in a regression format can be ascertained by systematically moving around where your 0 points are. It's a nice thing to know regarding how it works. Okay, we go to regression. We go to process. I'm going to go ahead and just work from the initial data. I'm going to put in sentences Y. I'm going to put in just world as my moderator. I'm going to put in attractiveness as my X. Remember that I'm using model 1 to refer to the interactions. Model 1 to get interaction effects. On my options, I'm going to request centering of all variables that define products, which happen to be continuous variables in this case. I'm going to go ahead and do the traditional conditioning values of -1 standard deviation at the mean and +1 standard deviation, as I've been talking about. I'm also going to ask for the Johnson-Neiman output. Over here, I'm going to ask it to generate the code for visualizing my interactions, and I'm going to ask it to test for the X by M interaction, although that really is only meaningfully not redundant when you have a categorical variable. Let's run. Here's my output, and it is essentially what I had before. This equation starts off assuming that since the data is centered, that you're at the mean on just world beliefs when you're evaluating attractiveness, that you're at the mean on attractiveness when you're evaluating just world beliefs. And just as we saw before, attractiveness is statistically significant. There's that -1.81 if you round off to the second decimal. And the other terms is as we've seen it before. Here's my test of the interaction. It's showing it's significant at 0.0443, but that's redundant with your interaction term up here of 0.0443. Here's your conditional effects, and this is going to give you exactly the same thing that I got from that little old program that I ran. It's showing when just world beliefs is below the mean by 1 standard deviation, which was a value, the standard deviation was right around 2.69 or 2.7 rounding off. So when it's below the mean by 1 standard deviation, you get a effective attractiveness of -0.7396. That's non-significant. When it's at the mean, which is a value of 0, it is -1.81, as we've repeatedly noted, and that effect is significant. And here, where just world beliefs are above the mean by 1 standard deviation, the effective attractiveness, the slope, is -2.87. So the more attractive, the lower the sentence, and less number of months that the person is sentenced to jail. and that is statistically significant. Okay, so that's the basics. What does the Johnson-Neiman do? The Johnson-Neiman more precisely is going to tell you, well, first of all, let's look here at these values. We notice that when we're at the mean on just world beliefs, the effective attractiveness is significant, and above the mean on just world beliefs is significant, but not when we're below the mean. So somewhere below the mean and at the mean, we switched from having slopes that were non-significant to significant. What the Neiman-Johnson technique did was to essentially just map out a whole bunch of those points so that you could find a point where it's separated. So you'll notice that it actually starts with values further away than 1 standard deviation. And looks like it's starting, somewhere in the neighborhood of 1.5 standard deviations, just guessing. And so that's minus 3.18. It's non-significant, non-significant, non-significant. Here I'm getting really close to what I have here with being below the standard deviation, being below the mean by 1 standard deviation, and it's still non-significant, and then right here, minus 1.4379. We get significance right there at a value of 0.05, right? So we're below the mean by 1.4379 standard deviations. So that's the precise point at which it flipped, a point in between these two. That's all the Johnson-Neiman is telling you. And so it allows you to basically designate that point where the flip occurs, because you notice that it's remained significant all the way through. Now, interactions can be more complicated, and you can go from positive to negative effects. So it's possible that you could start off non-significant, get a range of values that are significant, and become more significant again. For example, if you had a pattern that resembled a complete crossover interaction. A complete crossover interaction would more likely give you effects that start off giving you effects that were significant, then a range in which they're not significant, and then go back to a range in which they are significant. Let's go ahead and grab this program here, copy, open up syntax, paste it. So process has written an SPSS program. We're going to run that program. And here's the graph that we get. Double click, do a double left click, bring it up, and go over here to add fit line at subgroups. And there's your fit line, and that's what you're going to work with. The way that I did this was to grab this, copy, pull it over into PowerPoint, paste it, and then I started cleaning this stuff up. There's little tricks that you can do, such as, doing a white box and then moving the white box so it covers up material. Better, doing a text box that's white, pasting it over tract and sentence and writing that out more nicely. But I don't want to waste your time showing you those little things that you can do in PowerPoint. But I will note that if I go to insert and get a simple line, I can basically draw my own line that runs in the middle of these slopes. And so what I did was to basically estimate approximately where the that slope would be for the Neiman-Johnson technique that would separate these from one another. This was more easily done using the unstandardized version. So if you look at my graph that I have here, these are using standardized values. And so you have negatives, a negative standard deviation, one standard deviation below the mean, and a standard deviation above the mean. And when I did my graph here, you notice that I'm using not the standardized values, but the unstandardized values that give you the true feeling for the scale. So here's what's really nice about Process is that it's so easy to take care of issues of centering and to also view the data uncentered. Going back to Process, I'm going to go back to Options. I'm going to click No Centering. And here it is, the data uncentered. Notice that the main effect for attractiveness looks like it's non-significant now. And it looks like the main effect for just world beliefs is significant. But that's because just world beliefs become significant when attractiveness is extremely low, which the 0 point picks up, even though it's not a valid 0 point. The scale goes from 1 to 10, not 0 to 10. When we look over here, it's conditioned the effects though, so that we can see that when you're 1 standard deviation below the mean on just world beliefs, the effect is not significant, exactly like we've seen before. When you're at the mean on just world beliefs, which is 4.8148, here you get a true indication of your simple main effect. Not just the simple main effect at that value, but what you could refer to as the main effect for attractiveness, a minus 1.81, which is significant. And 1 standard deviation above the mean, again, it is statistically significant. Here you see, this is really nice, the full range of the values on just world beliefs. They go from 1 to 9. That's the full scale. And what's happened here is that Johnson and Neiman have gone point by increment by increment, changing that, but then they've narrowed down exactly the point at which P is 0.05, and thus gives you the cut point at which below that on just world beliefs, being low on just world beliefs, attractiveness has no impact. Above that on just world beliefs, attractiveness does have an impact. It specifies up here what that value is, and it tells you that 37% of all possible slopes, because there's even more slopes than what's represented here. It's really an infinite number of slopes that appear in a fanned out pattern. And it's telling you that 37% of those slopes would be non-significant. 63% of the slopes are significant going above that point. So that is a real nice addition of specification. And again, what I did was to take their graph in the unstandardized form and then estimate where that point was, note the point, the cut point in my text, and note that 63% of the slopes above that are statistically significant, 37% of the slopes below that are non-significant. And that refers to the slopes as we see them going across from the low on attractiveness up to high values on attractiveness. What we don't see is this cut point here. Where did that come from? So if I go back to process and take attractiveness out, take just world out, take just world and put it as my focal predictor, take attractiveness and stick it as my moderator, and rerun that analysis. I now see that looking at the Neiman or Johnson-Neiman values, that they're going from 1 to 10 on attractiveness. The effective just world beliefs are significant at the lowest values of attractiveness. They stop being significant at 3.34. 3.34. So 33% of the effects were significant on the below side. 67% above that are non-significant. What I did to represent that in this graph over here was to basically say, okay, I'm going to find that value of 3.34 approximately over here, so just below 3.5. Basically created a box where I shaded that area in, left this white, and then put in a designation that said 67% of the values going this way, non-significant, 33% of the values going this way are significant. This highlights that the significant region is really right in here where there are big differences as a function of the combination of the defendant's attractiveness and the judge's belief in a just world. Down here, we can see this from another perspective. I can grab hold of that. There we go. I'm going to copy that program and paste it. Run that program. Double click. So left click. Put those values in. And so what I'm seeing is the slopes um, at around, let's see, it's 7.84. This slope here is non-significant. This slope at the mean of 5 is non-significant. So you got to figure out, interpolate, here's a value of 2.23, here's a value of 5.04. So where in there would be a slope of right around 3.34, and then draw that slope, and above that, that's your significant region. Below that, that's your non-significant region. So that's that's from the perspective of using just world beliefs as your key predictor and attractiveness as the moderator. Rather than doing two graphs, what I did was to basically take that notion and integrate that information here um, with respect to the graph that I think makes the most theoretical sense, that I'm looking at the defendant's attractiveness as moderated by the judge's belief in a just world. And so then integrated that by shading in this area and making that note down here. Okay, so that's using process. There is one more graphic tool. If you go to two-way unstandardized graph um, in Excel, they have there's a little tool in there that I picked up off the web that's very nice. What you need to do is to do it centered though, which I had as attractiveness. I'm going to go ahead and put this back around the way that I had it to begin with. Attractiveness, belief in a just world. So you name your independent variable, you name your moderator, you only put in information in the yellow cells. Here was our equation. The one thing I'm going to switch around is putting my 0.715 there for the moderator, my minus 1.81 there for the predictor attractiveness. I have my interaction term in there, and I put my constant here. And this gives me a nice little representation of the graph. A nice thing about it is that it puts it in black and white. I can go ahead and make one of the lines dotted and the other one solid. It doesn't give me the middle line, which is one thing that I don't like about this. So I've often gone to actually putting, building my own Excel programs to fiddle with the graphs. But this is a fairly nice one, though, nonetheless. So it's basically giving you the same information, generally speaking, just not as much detail. But it works. That is it for now. If you have questions, please let me know and be glad to work on answering those for you. Take care.